This is Unit 1.9, Acids, Bases and Salts. So if you have your booklet of notes in front of you, ready to work through this. The first part of this topic looks at indicators, which hopefully you'll remember from first year. And just remember that indicators, they're solutions which change colour depending on whether they are in acids or in alkalis. And the reason that we need indicators is because often acids and alkalis are just colourless solutions that look a bit like water, and so it's very hard to tell them apart just from looking at them. In fact, it's impossible. So we need an indicator to tell us whether it's acidic or alkaline. And so the first indicator you need to know about is litmus paper, and again you would have covered this in first year. And litmus paper comes in two forms. It comes in red litmus paper and blue litmus paper. And the thing to remember with litmus paper, how you can remember which colour it turns, is the fact that litmus paper is always red in acids and always blue in alkalis. So no matter what colour it starts, it's always going to be red in acids, always going to be blue in alkalis, and then in neutral solution, it's whatever colour it started with. So going by that theory, red litmus paper, what colour is it going to be in acid? Well, it's always red in acids, it's going to be red. What colour will it be in neutral? Well, it stays the colour it started in neutral, so that's going to be red. And what colour will it turn in alkali? Well, litmus paper is always blue in alkalis, so it's going to be blue. With blue litmus paper, remember, litmus paper is always red in acids. It's going to be red in acid. What colour is it in neutral? Well, it stays whatever colour it started. So it's going to be blue in neutral and always blue in alkali. So it's going to be blue in alkali. So always remember that. Always red in acid, always blue in alkali, and then for neutral, it's whatever colour it started as. But litmus paper has a bit of a disadvantage in that it doesn't tell us how strong an acid or an alkali is, or how weak it is. It just tells us whether something is an acid or an alkali. But also you can't conclude from your results whether, say for example, you just took red litmus paper. If you got red litmus paper and your solution turned your red litmus paper red, you couldn't tell whether your solution was acidic or whether it was neutral. You would need to use a combination of both red and blue litmus paper to confirm that it was either neutral, if it was red and blue and blue, or if it was acidic, if it was red in both of those types of blue litmus paper. So that's a big disadvantage as well. So you can't, but the main one is that you can't tell how strong an acid is in litmus paper. A better indicator to use is universal indicator paper, as it gives us a range of colours and that tells us the strength of an acid or an alkali. Now hopefully again you'll remember this from year 8. So the pH scale gives us not only colours but numbers that represent the strength of an acid or an alkali. So if you put universal indicator paper in and it turns bright red, well you can tell that it's a very strong acid. On the other end of the scale, if you get purple, you can tell that it's a very strong alkali. The pH scale is a little bit funny in that we start off with very strong acids. Those strong acids then get weaker and weaker and weaker until a particular number, and that number is 7. 7 is the crossover point between acids and alkalis, and pH 7 is neutral. Once we go over to the other side then, we're into the alkalis, and alkalis get stronger and stronger and stronger until they get to 14. So we can say that the pH is a bit like a bow tie scale, strong at either ends and getting weaker and weaker as it goes in towards the middle, 7 being the crossover point of neutral. So these are your strong acids, your weak acids. These are your weak bases or weak alkalis, and then strong bases or strong alkalis. The method of using universal indicator paper is very important. This second point is in bold because people often forget it, but it's essentially the most important part of the process. So you say that using a glass rod, you dip that into your solution and you apply 1 drop to your piece of universal indicator paper. And then this second step is the most important step. You then have to take your universal indicator paper and compare it to the colour chart to determine your pH, because Now I might get a kind of yellowy green, but not be able to tell whether it was pH 2, pH 3, pH 4 or pH 5. So I need to take my paper and I need to compare it to the chart in order to get a number. And then that number can give me a better idea of whether my acid is strong or weak. So we have different intervals that we separate our acids and alkalis into depending on their strength, and you do need to know these intervals. What I mean by that is that 0 to 2 are your strong acids, 3 to 6 are then your weak acids because we are approaching neutral, which is 7, so 7 is neutral. And then we move into our alkalis. But close to neutral, our alkalis are weak alkalis. And then 12 to 14, those are our strong alkalis. So you need to know these numbers. So learn 0 to 2, 3 to 6, 7, 8 to 11, and then 12 to 14. And you've got some examples down the right hand side of those different types of acids and alkalis. So universal indicator paper is a better indicator than litmus in that it gives us an idea of the strength of acid or alkali, but it still only gives us whole numbers of pH numbers. And so a more accurate way of determining the strength of an acid or an alkali is by using a pH meter. pH meters can give us a value for the pH of a solution to either 1 or 2 decimal places, so it is much more accurate. So if you're asked in an exam, what is the most accurate way of measuring the strength of an acid or alkali, you can say that it's a pH meter. Now it's a bit like thermometer is a thermometer that measures the temperature of a solution. A pH meter measures the pH of a solution. So we can measure the strength of an acid or alkali using the pH scale. But concentration is another way of describing the strength of an acid or alkali. It tells us how concentrated an acid is. We describe a concentrated acid as a strong acid, or a dilute acid as a weak acid. And the units of concentration are in moles per decimeter cubed. 1 decimeter cubed is the same as 1 litre. So essentially we're saying how many moles, which is a unit of measurement in chemistry that you'll look at next year, how many moles of that solution are in 1 litre? How many moles of that acid or alkali are in 1 litre of a solution? And so, for example, you might have a solution that has a concentration of 1 moles per decimeter cubed, and you might see that labelled on bottles of acids or alkalis. It can also be abbreviated to 1 molar, which is 1 capital M. If you then had a solution that was twice as strong as that solution, it would simply have a concentration of 2 moles per decimeter cubed, twice as strong as a solution that was 1 mole per decimeter cubed. And if it was half as strong as our 1 mole per decimeter cubed solution, its concentration would be 0.5 moles per decimeter cubed. What we need to look at now is what actually defines what an acid or alkali is. An acid simply are substances that dissolve in water to produce hydrogen ions. Hydrogen ions are H+, and we give them a state symbol AQ. Remember that AQ is equal to aqueous, which really means that it's dissolved in solution. And we need that state symbol there because it's only when acids dissolve in water that they produce these hydrogen ions. So it's dissolved in solution, dissolved in water, and it's hydrogen ions, so it's H+ AQ. And that's what determines how strong an acid is, these H+ ions. The more H+ ions I have, the stronger the acid. Alkalis, on the other hand, dissolve in water to produce hydroxide ions. If you look in the back of your periodic table, you'll see that hydroxide is OH-, and again we use the state symbol of AQ because these are dissolved in water. And similarly to acids, the more hydroxide ions there are in a solution, the stronger the alkali is, the more concentrated. the alkali is.
The next part of your notes talks about what happens when you mix an acid and an alkali together. What you're doing is you're taking something from this end of the scale, you're reacting it with something from this end of the scale. What happens is that they react together and they form a neutral solution. They meet somewhere in the middle. Now it depends on the relative strength on the acid and the alkali. You have to add just the right amount. But if you add just the right amount, then you'll form a neutral solution. And the way to look at this is that an acid plus a base or an alkali, and we will describe the difference at the bottom of this page, they react together to give you a salt plus water. And anytime you see that type of reaction, i.e. one that produces salt and water only, then that's a neutralization reaction. Now the salt will differ depending on the acid you use and the alkali that you use. But if a salt and water are produced, then it's neutralization. And a salt will be something like potassium chloride or sodium sulfate, that sort of thing. A metal chloride or iodide or bromide, or a metal sulfate. And we can represent neutralization by an ionic equation that I've told you about before. This would be worth 3 marks in an exam if you were to be asked it, and so you should be very familiar with this equation. And what essentially is happening is we said that all acids dissolve in water to produce hydrogen ions. And it's the hydrogen ions that react with the hydroxide ions from alkalis. All alkalis dissolve in water to give hydroxide ions. And having a look even at that formula, you've got 2 hydrogens and 1 oxygen. So what they actually form is water. So if you think back to your ionic equations, what we've left out of this are our metal ions and the ions of our salt. So those are actually spectator ions. And so actually what's happening, the only thing that's really happening in neutralization is that your hydrogen ions are reacting with the hydroxide ions from the alkali to give water. Anything else involved in the process is a spectator ion. So please be very, very familiar with that equation. Practice writing that equation a good few times. It's worth 3 marks, and if it's asked, you will just be simply asked to recall it. And it'll be an easy 3 marks, so please take the time to learn that. And then finally, to do with neutralization, you do need to know the difference between a base and an alkali. And a base, by definition, is something that will react with an acid to produce a salt plus water only, i.e. something that will neutralize an acid. And these are metal oxides or metal hydroxides. So, for example, sodium oxide, which is Na2O, or sodium hydroxide, which is NaOH. Also things like potassium oxide, which are K2O, or potassium hydroxide, KOH. Magnesium oxide would be another example because it's a metal oxide. Its formula this time would be MgO because it's in group, magnesium is in group 2. Or magnesium hydroxide, which would be MgOH2. So anything that's a metal oxide or a metal hydroxide is a base. But sometimes bases can be insoluble. But with alkalis, they're always soluble. So, listen carefully to this. All alkalis are bases, but not all bases are alkalis. We say that again. All alkalis are bases, but not all bases are alkalis. So I think of it like a big circle. You have a circle of bases, and everything in here are bases. Then there's a separate circle within that circle that are alkalis. And they are the soluble type of bases. So if it's insoluble and it reacts with acid to produce salt and water only, then we call it a base. If it's soluble and it reacts with acid to produce salt and water only, then we call it an alkali.
Then we move on to our reaction of acids, and we're going to look at our reaction of acids with metals, with metal oxides and hydroxides, and metal carbonates as well. And it's best to separate out your learning of these three types of reactions because there are similarities between them, but there are also big major differences. And the main thing to focus on in terms of preparation for your exam are the general equations of what happens with these types of reaction, and also your observations of what happens for these reactions. And almost if you knew the general equations, you could work out some of the observations based on the products that are given. So let's start with our reaction of metals with acid. So when a metal reacts with acid, a salt plus hydrogen are produced. And this is a reaction that you would have studied from year 8 and then also again in year 10. So when a metal reacts with acid, we always get a salt, and the name of that salt differs depending on the metal and the acid that you're using. And then we always get hydrogen as our side product. And when we're naming the salts, we have a few rules that apply. The first part of the name comes from the metal, and the second part of the name comes from the acid that we use. So first part of the name comes from the metal, and that name remains unchanged. Second part comes from the acid, and the ending changes depending on the acid that we use. Hydrochloric acid changes its ending to chloride. Sulfuric acid changes its ending to sulfate, and that's all given here. The important thing here is your formula for your acids. HCl is the formula for hydrochloric acid, and you need to know that formula. And H2SO4 is the formula for sulfuric acid, and you need to be familiar with that. Over on the right hand side, you have your ions, and these will help when writing the formula of your salt. So chloride salts, because it has a charge of minus, the valency of chloride is 1. Because sulfate has a charge of 2 minus, the valency of sulfate salts are going to be 2. And that will help when you're writing the formula of your salts. Think how we form these ions. Remember we said that all acids, when dissolved in water, form hydrogen ions. So actually what happens when I dissolve hydrochloric acid in water, I produce hydrogen ions because it's an acid. And then there are my chloride ions. And we can say that those are aqueous because I've dissolved them in water. Same thing with sulfuric acid. It's H2SO4. It dissolves in water to give me hydrogen ions because it's an acid, and also sulfate ions. But have a look here, you've got H2, and that means I form 2 hydrogen ions for every 1 sulfuric acid. So let's have a look at naming, an example of naming those salts. Well, here we've got sodium reacting with sulfuric acid. First part of the name we said comes from the metal, and it remains unchanged, so it's just sodium. Second part of the name comes from the acid, and sulfuric acid changes its ending to sulfate, and so the name of our salt is sodium sulfate. This is the salt. And our other product from our general equation is hydrogen. So all of these reactions of a metal with an acid will give us a salt plus hydrogen. So they will all end with plus hydrogen. So you should check that when you have a metal reacting with acid, that you always have written hydrogen on the right hand side of the equation as a product. So we then looked at some specific examples of metals reacting with acid, and we looked at what observations we see when these reactions take place. And I have a video online from last year that that contains some of these reactions videoed, both of the metals and acids, metal oxides and acid, and metal carbonates and acid. So if you want to see these reactions in action, then look up that video from last year. So when we're thinking of our observations, yes, you should be familiar with these observations, but it's also helpful to keep the general equation in mind. So we've got a metal plus an acid reacting to give us a salt plus hydrogen. So this gives us a clue for our observations in this, that we're producing hydrogen. Think to yourself, what form is hydrogen in? Well, it's a gas. And so if we've got a gas being formed in a solution of acid, then we're going to see bubbling happening because the gas is being released. So the first observation we're going to see here is that there's fizzing or bubbles of gas. You can refer to it either way. As our metal reacts, so in this case it's calcium, it disappears. We refer to it as disappearing. This reaction also releases a lot of heat. If you feel around the outside of the test tube, it releases a lot of heat. And then we are left, once the metal has all reacted, we're left with a colourless solution. Okay, products then, again, our general equation is going to help us. So we're going to produce a salt and we're going to produce hydrogen. First of all, we have to name our salt. And the first part of the name comes from the metal. And in this case, our metal is calcium and its name remains unchanged. So the first part of our name is calcium. Second part of the name comes from the acid. And the name of the acid changes from hydrochloric acid to chloride, and you can colour code it in your notes to help you if that helps. So calcium chloride is the name of our salt, and what else is produced? Always hydrogen. With the second reaction, we see exactly the same observations because we've got a metal reacting with an acid again. So we're going to see fizzing due to the production of hydrogen. The magnesium is going to disappear into the solution. There's going to be heat released, and we're going to form a colourless solution at the end of it all. Okay, so what are my products? Again, I form a salt and I need to name that salt. The salt, first part of the name comes from the metal. In this case, my metal is magnesium. Second part of the name of my salt comes from the acid. The name is sulfuric acid, and so it changes its ending to sulfate. Hydrochloric acid changes to chloride, sulfuric acid changes to sulfate. What is my other product? Well, it's always hydrogen. Okay, so we're ready now to write some equations for what is happening here. And first of all, we're writing equations for the reactions that are in the table. And very simply, we just need to write our reactants on the left. So that's calcium and hydrochloric acid on the left. And that's producing our salt, which is calcium chloride, and hydrogen. Okay, again, that fits our general equation of metal plus acid gives us a salt plus hydrogen. Then we have to write our balance symbol equation. And this is a little bit more difficult than writing the word equation. But again, we're going to do this step by step, just as we did when we were practicing writing equations. And you are very likely to get one of these types of equations, either a metal with an acid, a metal oxide with an acid, or a metal carbonate with an acid. Those types of reactions we'll look at after this type, but you need to be familiar with this type of equation. The most important thing is to know your general equation, and you can work from that. So when we're writing a balance symbol equation, remember we take each term of our equation and we convert it into the formula. So calcium, first of all, what's the formula for calcium? Well, it's just Ca. Hydrochloric acid then, told you on the previous page that you need to be familiar that its formula is HCl. Calcium chloride then, well, calcium chloride, it's a compound and I need to do swap and drop for it. So I've got calcium and I've got chlorine, so I write those two symbols down. Then I need to write down their valencies, which I get from their group numbers in this case. Calcium is group 2, so its valency is 2. Chlorine is group 7, so its valency is 1. Then when I swap and drop, you can see that my formula is going to be CaCl2. Plus hydrogen. Now you might be tempted to just write hydrogen as H. But remember, hydrogen is one of our diatomic elements, and so we need to write it as H2. You need to remember that, otherwise the balancing of your equation is going to go wrong. So we now need to balance it, and in order to do that we make a list of what elements we have on each side of the equation. So we have calcium, we have hydrogen, and we have chlorine. We copy that list on the other side in exactly the same order so we can compare them. Firstly, we have 1 calcium, we have 1 hydrogen, and we have 1 chlorine on the left hand side of the equation. On the right hand side, we have 1 calcium, 2 hydrogens, and 2 chlorines. So you can see that my hydrogens and my chlorines are unbalanced. So firstly, I need 2 hydrogens on the right hand side. And remember, at this stage, when balancing, you can only put big numbers in front of the whole formula. Big numbers in front of whole formula. Anything else you do, be it put a number in between a formula or put a number at the end of a formula. For example, if I saw that I needed 2 chlorines and wanted to just put a 2 there, that changes the formula of the substance and that is incorrect. So I can only put big numbers in front of the whole formula. I need 2 hydrogens, so I need to put a 2 in front of the only thing on the left hand side that contains hydrogen. I then update my list as to what that affects. It affects everything in that formula by multiplying it by 2. So I now have 2 hydrogens and I now have 2 chlorines. So what we can see is by putting that big 2 in front of the hydrochloric acid, I've balanced my entire equation. Okay, if you're not sure about writing that, go over that again and try it again, or even try writing it yourself on a separate piece of paper. Write out your word equation and try and work through the balance symbol equation underneath. Okay, then we have magnesium and sulfuric acid. Again, you can just get your products from the table above. But we know that when the metal reacts with acid, we're going to get a salt. In this case, first part of the name is magnesium from the metal, second part of the name comes from the acid, and sulfuric acid changes its ending to sulfate. The other product is hydrogen. Okay, again, you just write this in all one line. The only reason I'm writing acid and sulfate on the lower line is just for room. When you're writing equations, make sure it's all in one line. Okay, so my balance symbol equation, I want to convert each of these terms into a formula. So first of all, magnesium, its formula is Mg. Next, I have sulfuric acid, and again, you need to be familiar with the formula of sulfuric acid, which is H2SO4. Next, I have magnesium sulfate. So I need to do my swap and drop to get my formula for magnesium sulfate. And I'm going to do it over here just so I have enough room to do my working out. So firstly, I need to write down my formula. And perhaps I'll write my name so I can work underneath it. So magnesium is Mg. Sulfate, it appears in the back of your periodic table. If you're not familiar with it, look at it now. It appears in the back of the periodic table as SO4 2-. The 4 and the 2- are very close together, but you need to remember to separate them out when writing your formula. First thing I do is write down everything apart from the charge. Everything apart from the charge. So I need to write down SO4. I then use my charge to get my valency. So my charge is 2-, that means my valency is 2. For magnesium, to get the valency, I just look at my periodic table. I see that it's in group 2, so its valency is 2. My ratio of my valencies is 2 to 2, so I can cancel that down to 1 to 1. Then when I swap and drop, I'm going to end up ignoring my 1s, and so my formula is just MgSO4. But it's important that we write those together. So it's MgSO4 for magnesium sulfate plus hydrogen, which is H2, because it's diatomic as discussed above. Now you can make a list for this, and you should make a list in the exam to check that it's balanced, but on quick looking at this equation you can see that it is balanced. I've got 1 magnesium on either side, 1 sulfur on either side, 2 hydrogens and 4 oxygens. But again, in an exam, make a list to check that it's balanced. Before we move on to practicing more of those equations of metals reacting with acid, we need to have a look at what's happening in the test for hydrogen. So you may remember from junior school that testing for hydrogen is the Squeaky Pop Test. So we know that when a metal reacts with an acid, we produce a salt plus hydrogen. We need to be able to test that that gas given off is actually hydrogen, because it could be another gas like oxygen or carbon dioxide. So we need to be able to test that it is actually hydrogen. And that can also be a confirmation test for this reaction, because it's this reaction in particular that produces hydrogen. So we can tell that it will be a metal reacting with acid. So it's referred to as the Squeaky Pop Test, but you need to know the procedure of how you test for hydrogen. And sometimes this is done in different ways, but in an exam, if you're asked for the method to test this gas, you need to say that you apply a lighted splint to a test tube containing hydrogen and a popping sound will result. Essentially that is you taking a test tube and it's full of hydrogen. You're applying a splint to it that is lit, and a popping sound will result. Okay, so collect some hydrogen, and we can do this in the lab, but if we're doing this reaction and we have our test tube rack containing our test tubes of metals reacting with acid, and then we can hold another test tube, perhaps a boiling tube that is bigger, over the top of it. The hydrogen will collect in that test tube, and then we can test it using our lit splint. Okay, so be familiar with that method if you're asked to recall it in the exam. But what you also need to look at is what is actually happening when you are carrying out your Squeaky Pop test. And the reason for the pop is that it's a mini explosion of hydrogen. So hydrogen is reacting with the oxygen in the air and it is exploding. So hydrogen, which is H2, is reacting with the oxygen in the air, which is O2. And what do we get when we react hydrogen and oxygen? Well, we get water. And if we were to include our state symbols, we know that hydrogen is a gas, so that's G. We know that oxygen is a gas, which is G. And we know that water is a liquid, which is L. Now, that explains the observations that we see in this Squeaky Pop test. Because when you apply your lighted splint and your popping sound results, what you'll be left with is some condensation around the walls of the test tube. A colourless liquid you'll observe, and that colourless liquid is water, because your hydrogen has reacted with oxygen to produce water. So if you start with a perfectly dry test tube, you collect your hydrogen and then apply your lighted splint, you'll notice a colourless liquid around the walls of the test tube, and that is the water that you form as a result of this reaction, the explosion of hydrogen. Okay, so there are a couple of other examples of reactions of metals and acid that you should try writing your equation. So first of all, you need to think about what the name of your salt's going to be and what other product you're going to produce, bearing in mind your general equation of metal plus acid gives you a salt plus hydrogen. That should always be in your head. So have a go at writing these two equations. Pause the video and give them a go, writing your word equations and your balance symbol equations. And then you can replay the video and I will go through them and give you the answers. But try them yourself so that you can get practice in doing these types of equations and then check your final answer. So when we react aluminium with hydrochloric acid, we produce a salt plus hydrogen. The salt is going to be aluminium chloride. First part of the name from the metal, second part of the name from the acid. And our other product is hydrogen for this type of reaction. Then when you're writing your balance symbol equation, you perhaps find this difficult. It's a difficult equation to balance. First of all, aluminium is Al. Hydrochloric acid is HCl. Aluminium chloride, I need to do my swap and drop for. So it's aluminium and then it's chlorine. Aluminium is in group 3, so it has a valency of 3. Chlorine in group 7, so it has a valency of 1. So when we swap and drop, we get AlCl3. Our other product is hydrogen, which is H2, because it's diatomic. Looking at this equation, you can see it's not balanced. So we need to make a list of the elements we have on both sides of the equation. So we have aluminium, we have hydrogen, and we have chlorine. So on the left hand side we have 1 aluminium, we have 1 hydrogen, and we have 1 chlorine. Over on the right hand side we have 1 aluminium, 2 hydrogens, and 3 chlorines. So you can see that again it's our hydrogens and our chlorines that are unbalanced. Now you can go through the process of putting a 2 in front of your hydrochloric acid to balance your hydrogens, but you can automatically see that that's not going to balance your chlorines. It's a quick way to do this, and if this doesn't make sense to you, please do it the long way. You will get there eventually. But any number that we put in front of our hydrochloric acid is going to multiply the hydrogen and the chlorine by the same number. But we have 2 hydrogens here and 3 chlorines here. So what we're thinking of when we're balancing our hydrogens and chlorines is what is the lowest common multiple of these numbers. What's the lowest common multiple of these numbers? Because that number that we put in front of HCl is going to multiply both of them. The lowest common multiple of 2 and 3 is 6. So I need 6 hydrochloric acids. That means that my number of hydrogens is 6 and my number of chlorines is also 6. So how am I going to get 6 chlorines on the right hand side? Well, I've got 3 chlorines in my aluminium chloride. So I need to think what number multiplied by 3 is going to give me 6. And that is 2. If I put a 2 in front of the aluminium chloride, I now have 2 aluminiums. And I have 2 times 3, which is 6 aluminium, or 6 chlorines. Then I need to balance my hydrogens on the right hand side. And I need 6 hydrogens, so I need to think what number times by 2 is going to give me 6, and that number is 3. So I now have 6 hydrogens on the right hand side. The last thing I need to balance is my aluminiums, and it's good to leave the things that are on their own to the very end, because whatever number, you can put whatever number in front of them to balance your equation. And that's my aluminium. I need 2 of them, so I put a 2 here, and that gives me 2 aluminium. So there's your balanced equation. That is very difficult, and they're not likely to give you one that difficult, but it's good practice in balancing equations. Okay, then zinc plus sulfuric acid. So we have zinc plus our sulfuric acid gives us, and the name of our salt, the first part of the name is going to be zinc from the metal, and then sulfate from the acid. Zinc sulfate plus hydrogen. Then forming our balance symbol equation, well, zinc is Zn, sulfuric acid is H2SO4, zinc sulfate we need to do our swap and drop for. Zinc is in the transition metal block, and so it doesn't have a group number, but if you look on the back of the periodic table, it appears as Zn2+. So when we're writing our formula, we write down zinc, and its valency is 2. Sulfate appears in the back of the periodic table as SO4 2-. First thing I do is write down everything apart from the charge, including that 4 at the end. You must include that 4 after the oxygen, otherwise you won't get the right formula. And our valency is 2 because of the charge of 2-. I can cancel that down to Zn1, SO4 1. And so when I swap and drop, I'm going to end up ignoring my 1's. So my formula is ZnSO4. You need to do your swap and drop to double check that, because it may not end up as a 1-to-1 ratio. And so you might need to include a 2 or a 3 after the zinc or after the sulfate. And remember to use brackets if there's a number after your molecular ion. So if there was to be a number that we were swapping down to our sulfate, we would need brackets. Plus hydrogen is plus H2, and again you should make your list to double check that this is balanced, but a quick look at it will tell you that this equation is balanced. So you need to be familiar with those, so you could even give yourselves a couple of other examples. So choose a metal like sodium, react it with an acid, one of your two acids, hydrochloric acid or sulfuric acid. Make sure you can write a word equation for it, so name the salt and then always include plus hydrogen at the end. And then try writing balance symbol equations from that. The next type of acid reaction that you need to be familiar with is the reaction of acids with not metals, but metal compounds of metal oxides and metal hydroxides. What we find with this is that again they produce a salt, but our side product is not hydrogen, our side product is water. So when a metal oxide reacts with acid, we produce a salt plus water. It's the same equation with a metal hydroxide and acid. We get a salt plus water. It's the same general equation for both of them. And again, we need to name our salts, and it's done in a very similar way to the previous type of reaction of acids with metals, in that the first part of the name comes from the metal oxide or the metal hydroxide, but we just drop the oxide or hydroxide, so essentially we're looking at the metal used. So have a look at this example. We used sodium hydroxide in this example, and the first part of our name of the salt ends up being sodium. So just drop the hydroxide essentially, and the first part of the name is sodium. Second part of the name, as before, comes from the acid, and hydrochloric acid changes its ending to chloride. So our salt is sodium chloride. So the salt is named in exactly the same way as above, but just drop the hydroxide or oxide from the metal compound name. So you can see that in the reaction that we have here, and this is the one example that you need to be familiar with. So we've got copper oxide reacting with sulfuric acid. So copper oxide reacting with sulfuric acid. First part of the name comes from the metal, which is copper. Second part of the name of the salt comes from the acid. And we've got sulfuric acid, so it changes its ending to sulfate. With this reaction, again, if you want to see this reaction happening, then look up my video from last year on this topic, and you'll see it happening. Basically, we have to put copper oxide in a solution of sulfuric acid, and we have to heat it in a hot water bath because copper oxide is quite unreactive. But when it starts to react, we see that the colourless solution of the acid changes to blue. And that's because initially we were working with sulfuric acid, which is colourless, but we are forming copper sulfate which is blue. And that's why we see the blue colour forming. You'll notice there are much fewer observations for this reaction, but again, as I said, you can link your observations back to your general equation. So think what I'm forming here. I've got a metal oxide reacting with acid to give me a salt plus water. The previous type of reaction we saw fizzing, and that's because we were producing hydrogen. But here our side product is water. And so there's not going to be any fizzing because we're not producing a gas, we're producing water as our side product. So that's why we see no fizzing with these types of observations. So be familiar with that. So if we're trying to write our word equation for copper oxide and sulfuric acid, we simply write our reactants on the left. So we've got copper oxide reacting with sulfuric acid. That's going to produce a salt, the name of our salt. First part of the name comes from the metal, which is copper. Second part of the name comes from the acid, which changes its ending to sulfate. And our side product is water this time. Okay, then looking to write a balanced symbol equation of it. For copper oxide, I'm going to have to do my swap and drop. Copper again is a transition in the transition element block. And so we can't get its valency from its group number. So look to the periodic table, back of the periodic table, and you should see that copper ions are Cu2+. That charge of 2+ means the valency of copper is 2. We then have oxide, copper oxide. Oxygen is in group 6, and so its valency is 2 also. So that can cancel down if I work this way. That cancels down to 1 to 1. So the formula of my copper oxide is simply CuO. Sulfuric acid, as we discussed before, is H2SO4. Copper sulfate, I then need to do my swap and drop again. So I'll do that down here. So I've got copper sulfate. Copper is Cu. Sulfate appears in the back of your periodic table as SO4 2-. Again, first part of doing this formula, you write down everything apart from the charge. So that's SO4 for sulfate. And then the valency I get from the charge. Charge is 2-, so that means its valency is 2. And just as we did above, copper forms copper 2+ ions, so its valency is also 2. That cancels down to 1 to 1. So then when I swap and drop, I'm going to end up ignoring my 1s, and so the formula of copper sulfate is CuSO4. So that forms copper sulfate CuSO4 plus water. So again, a quick look at this shows you that the equation is already balanced. You've got 1 copper here, you've got 1 oxygen plus 4 oxygens is 5, and then on the right hand side you've got 4 plus 1, which is 5, and 2 hydrogens on either side. So this equation is balanced, but again, make your list to double check. So over on page 11 we can see a series of other reactions of these type, a metal oxide or hydroxide reacting with acid. And what you need to do with this is always keep in your head the general equation. So that is that when a metal oxide or hydroxide reacts with acid, we get a salt, which we have to name, and then water. It's always going to be plus water at the end. So the first step in this is to always write your word equation. Never try to just jump straight to the balanced symbol equation. So with sodium hydroxide and sulfuric acid, first of all we can write the left hand side of our word equation very easily. I'm going to write it underneath this just so I have room. Sodium hydroxide plus sulfuric acid reacts to give me my salt, which we'll name in a second, plus water.
Okay, naming salts is very similar than with metals and acid. For the first part of the name, we look to the metal. Okay, and in this case, my metal is sodium. Yes, I have hydroxide after it, but I just ignore that part of the name. So the first part of the name of the salt is sodium. And then for the second part of the salt name, we need to look to the acid. And this time, it is sulfuric acid. And so the second part of my name is going to be sulfate. Remember that sulfuric acid changes its ending to sulfate. So you can see we can have a very similar salt name as we would have met previously with the reactions of metals and acid. Okay, so it's now time to form our balance symbol equation. And for quite a few of these, we're going to have to do our swap and drop. So sodium hydroxide, first of all, we need to do our swap and drop for that. So what we've got there is we've got sodium, and then we've got hydroxide. Hydroxide is one of our molecular ions, and you'll need to look to the back of the periodic table for that. You'll see that it appears as OH minus. So the first thing I do is write everything down bar the charge. In this case, that is OH. Okay, I then look to the charge for my valency. It's just 1 minus, so my valency is 1. Sodium, then, I just look to the periodic table for its valency, find which group it's in, and you'll see it's in group 1, and so it has a valency of 1. So when you swap and drop those, you get that the formula of sodium hydroxide is NaOH. Sulfuric acid is one you should just know, which is H2SO4. Okay, that's reacting to give us sodium sulfate. Again, I'm going to need to do my swap and drop for this. So I've got sodium, and then I've got sulfate, which is one of my molecular ions. Sulfate is SO4, 2 minus. Again, first thing I do is write down everything bar the charge. So I write down SO4. And then I look to my valency, or look to my charge for my valency. And I can see that my charge is 2 minus, and so my valency is going to be 2. Sodium, again, was group 1, so its valency is 1. So we can see when I swap and drop that, the 1 swaps to the sulfate, so I don't need any brackets because there's just going to be a 1 outside it. But you can see that the 2 from my sulfate is swapping to my sodium. So I'm going to end up with a formula of Na2SO4. Okay, after that I've got water, which is simply H2O. Okay, we can see from this that it's not balanced, and so we're going to need to balance it. Alright, so the first step is that we make a list of the elements that we have. So we have sodium, oxygen, hydrogen and sulfur, and then make that list on the right hand side. Okay, how many sodiums do we have on the left? We can see we have just 1. How many oxygens? Be careful with this. You've got 1 here and 4 here, so that's a total of 5. Hydrogens, again, need to be careful. I've got 1 with my hydroxide and 2 with my sulfuric acid, so that's a total of 3. And sulfurs, I just have 1. On the right hand side then, you can see that I have 2 sodiums. I have 4 oxygens here, but 1 with my water, so that's 5. I have 2 hydrogens, and I have just 1 sulfur. Okay, so you can see that my equation is not balanced, and it's probably easiest to start with sodium, since we have 2 on the right and only 1 on the left. Remember, at this stage we can only put big numbers in front of the whole formula. And so what I'm going to do is put a big 2 in front of my sodium hydroxide. Then it's really important that at this stage you update your list as to how many of each atom you have. So I've affected my sodiums, and now I have 2 sodiums. I've also affected my oxygens. So it's 2 multiplied by 1, which is 2 oxygens, plus my 4 that are here, which is a total of 6 oxygens. Hydrogens now have been affected as well. I have 2 times my 1 hydrogen here, that's 2, plus the other 2 here, which is a total of 4. Okay, so you can see I fixed my sodiums, but my oxygens and hydrogens are not balanced. If you look at hydrogens, I've got 4 here and 2 here. So I need twice as many on the right hand side. I fix that by putting a 2 in front of my water. I now have 2 multiplied my 2 hydrogens, and so I now have 4 hydrogens, and I now have 4 plus 2 times my 1 oxygen, which is 6 oxygens. So you can see my equation is now balanced, but we have to take that step by step. What I'd like you to do now is have a go at the rest of the equations on this page. So that's magnesium oxide and hydrochloric acid and calcium hydroxide and sulfuric acid. So pause the video for a second, give those a go, and then once you've tried them you can press play again and check through them. So the first example there is magnesium oxide and hydrochloric acid. We need to complete the rest of our word equation, and we do that by first naming our salt. Remember your general equation, we're forming a salt plus water. For our salt, we get the first part of the name from the metal, which is magnesium. And second part of the name from the acid. We've got hydrochloric acid here, and remember it changes its ending simply to chloride. Not hydrochloride, not anything else, just chloride. And we also then have water. Don't forget about your water at the end. So for my formula, I need to do a bit of swap and drop work. Magnesium oxide is simply using magnesium and oxygen. So don't overcomplicate this if it doesn't need to be. So you've got magnesium and then you've got oxygen. Magnesium is group 2, so it should have a valency of 2. Oxygen is group 2, so it should or group 6, so it should also have a valency of 2. We can see that that cancels down. Remember, we want our numbers in their simplest ratio. That cancels down to 1 to 1. Then when I swap and drop, I can see that those 1s will just cancel. And so I end up with MgO. Hydrochloric acid is simply HCl. And again, that's something you should be familiar with. Magnesium chloride then. Again, this is just a very simple version of my swap and drop. I use magnesium, and for chloride I use chlorine. Again, don't overcomplicate that. Magnesium is group 2, so it has a valency of 2. Chlorine is group 7, so it has a valency of 1. When we swap and drop that, we end up with a formula of MgCl2. And then we have plus water, which is H2O. Okay, we can see my equation's not balanced, so let's take some time to balance it now. I have magnesium, oxygen, hydrogen and chlorine. And then I write that list on the right hand side. Okay, counting up how many I have on each side. How many magnesiums do I have on the left? I have 1. I have 1 oxygen, 1 hydrogen and 1 chlorine. On the right hand side I have 1 magnesium, 1 oxygen, 2 hydrogens and 2 chlorines. I can very simply fix this problem by putting a big 2 in front of my hydrochloric acid. That now gives me 2 hydrogens and 2 chlorines, and so my equation is balanced. The next example we have is calcium hydroxide reacting with sulfuric acid. First thing we need to do to complete our word equation is name our salt. First part of the name comes from the metal, which is calcium. Second part of the name comes from the acid, which is sulfuric acid. Sulfuric acid changes its ending to sulfate, and so the name of my salt is calcium sulfate. And then, as always, we have plus water at the end. Okay, so we need to write our balance symbol equation for this. And we need to do our swap and drop for calcium hydroxide. So first thing is that we've got calcium. Second thing, we've got hydroxide. Remember, hydroxide is on the back of your periodic table. It's OH minus. First thing I do is write down everything bar the charge, and that's OH. And then I look to my charge for my valency, which I can see is going to be 1. Calcium is group 2, so it's a valency of 2. When I swap and drop that, you need to be really careful with this. Because the 2 is swapping over from the calcium, it's applying to the whole hydroxide. That means it needs to apply to the oxygen and the hydrogen. So to show that, we put the hydroxide in brackets. It's really important that you remember those brackets. You won't be able to balance your equation properly if you don't do that. Then we're using sulfuric acid, which is H2SO4. Calcium sulfates, I need to do my swap and drop again. I've got calcium, and then sulfate is SO4, 2-. So first thing, write down everything bar the charge, including that little number 4 at the end. So it's SO4. And then I look to my charge for my valency. My charge is 2-, so the valency is 2. Calcium is group 2, so it also has a valency of 2. Those number 2's are going to cancel down to 1 to 1. Then when I swap and drop, I will get CaSO4. There's no number outside the brackets, so I don't need to include them. It's just CaSO4 plus water on the other side. Okay, my equation is not balanced, so I need to make my list. I've got calcium, oxygen, hydrogen and sulfur. Calcium, oxygen, hydrogen and sulfur. Let's count up, and we'll need to be a wee bit careful with this. Calciums, I've got 1. Oxygens, this 2 multiplies everything inside the brackets by 2. So I've got 2 times by my 1 oxygen, which is 2, but then I've got another 4 here, so that is 6. Hydrogens, again, be careful with this. You have 2 times your 1 hydrogen here, which is 2, but I've got another 2 here, and that is 4. Sulfurs, I just have 1. On the other side then, a little bit simpler. Calcium, I've got 1. Oxygen, I have 4, plus my 1 here, which is 5. Hydrogens, I simply have 2. And sulfurs, I have just 1. Okay, so we can see that we need more oxygen and hydrogen on the right hand side. The only way I can fix that is by putting a 2 in front of my water. Now I need to update my list. I can see that I have twice as many hydrogens, so I've got 2 times by my 2 hydrogens, and that is 4. And then for my oxygens, I have 4 oxygens here, and then 2 times by my 1 oxygen here, which is 2. That's a total of 6, and we can see that my equation is now balanced. So for these types, it's really important ultimately that you remember this general equation. Metal oxide or hydroxide plus your acid gives you a salt plus water. And from this general equation, we can tell that this type of reaction, or reactions of metal oxides and hydroxides with acid, that this is a type of neutralization reaction, which it states at the top of page 11 here. The definition of a neutralization reaction is an acid or a base reacting with an acid to produce salt plus water only. Metal oxides and hydroxides, they are bases. Some of them are alkalis, particularly your metal hydroxides are alkalis because they are soluble. But the likes of your metal oxides sometimes tend to be insoluble, like copper oxide is insoluble, and other things are insoluble. And so when we're reacting a base here with an acid, and we're producing a salt plus water only. So this is a type of neutralization reaction by definition. So all of this type, the second type of reaction here, is a neutralization reaction. So any example of a metal oxide or a hydroxide that you get reacting with any acid is going to be a neutralization reaction, because it's always, by the general equation, going to produce salt plus water. So the last type of reactions of acids is acids with metal carbonates this time. And we'll have a look to see how our equation is a little bit different. And it's these general equations that are the most important things here. What we find when a metal carbonate reacts with acid is that again it produces a salt, but my side products are now water and carbon dioxide. Water and carbon dioxide. The easiest way to remember that is that your metal compound is called a carbonate. So I'm producing carbon dioxide. Okay, the main thing we'll do here is have a look at our equations, and then we'll come back to this in class next week. So you can see again we name our salt in exactly the same way as with the metal oxides and hydroxides. So the first part of the name comes from the metal, and so we looked in this case to see that it's copper, and so I write down copper and I just ignore the fact that it is carbonate. Then when I'm naming the second part of my salt, I'm looking at my acid, sulfuric acid, and so I change my ending to sulfate. So my salt in this case is copper sulfate. Let's have a look at some examples, and I will show you the reaction of these in school next week. First one we have is copper carbonate plus sulfuric acid. And just to let you know, copper carbonate is a green powder. It's a sort of turquoisey green, but it's just called green. And copper carbonate is green, and we'll see that next week. What we see with this reaction, and again you have to think of your general equation. So we can see from our general equation that we're going to produce a salt, water and carbon dioxide. And it's this carbon dioxide that I want to think of. What is carbon dioxide? Well, it's a gas. Anytime we are producing a gas, we're going to see bubbling. So even if you can't remember these observations in the exam, think what you're producing, and that should help you. So the first thing that we're going to have is bubbles of gas produced, or fizzing is fine. Second thing is common with our metal plus acid reaction, and that's the fact that heat is released. Similarly, where the metal disappears with the reaction of metals and acids, the solid disappears in this case, and the solid is copper carbonate, so the copper carbonate will disappear. And then finally, just as with the previous type, with copper oxide and sulfuric acid, we see a colour change here. So again, think about what you're going from and going to. So we start with sulfuric acid, and that's a colourless solution. We're then going to be going to a solution of copper carbonate, and perhaps at this stage it is, we could put in our products. So let's have a think of the salt that we're going to produce. Again, first part of the name comes from the metal, and so that's copper. Second part of the name comes from the acid, which is sulfuric acid, so it's going to be copper sulfate. We're then also, as our equation tells us, we're going to produce water and carbon dioxide. Okay, so looking at our salts, we can see that we're forming copper sulfate. We know that when copper is in solution, it is blue. So the colourless solution is going to change to blue, just as we saw with copper oxide and sulfuric acid. So colourless solution changes to blue. So we're thinking about what our products are and what we might observe from that. Calcium carbonate and hydrochloric acid, it's very similar. Again, think of what you're going to produce first of all. The name of our salt is going to be calcium from the metal, and chloride from the hydrochloric acid. As per our general equation, we're going to form water and carbon dioxide. So again, thinking of our products, we can see we're forming carbon dioxide. That means that we're going to have bubbles of gas produced. Again, we're going to see heat released and the fact that the solid disappears. The solid in this case is calcium carbonate. Calcium carbonate is just a white, either a powder or granule type form, and what we find with this is that the solution remains colourless. Above, the solution changed to blue because we had copper, but here we just have calcium as our metal, which forms colourless solutions. So the next thing we need to do is write our equations for these reactions. And again, always keep in mind your general equation when you're writing these equations, and I've written that at the top. So the first thing we need to do is name our salt. We can see the salt is the first product. So for the name of the salt, I get the first part of the name from the metal, which is copper, and just write that straight down. Second part of the name comes from the acid. Here I've got sulfuric acid, so the second name is going to be copper sulfate. Then I look to my general equation for the other products. I can see that I'm forming water and carbon dioxide, so I just simply write those in. Okay, now for my balance symbol equation. Again, we have to do a little bit of work with our swap and drop here. So for copper carbonate firstly. So copper is Cu, and carbonate appears in the back of your periodic table as CO3 2-. First thing with it is that I write down everything bar the charge, which is CO3. I then look to my charge for my valency. My charge is 2-, and so my valency is 2. With copper, it's in the transition metal block, so it doesn't have a group number. What you can do is look at the back of your periodic table and see that it's 2+. But also in this example, we're given the number in brackets. That represents the valency, which is 2. So it's finding your valency is the next step. We can see that our ratio here is 2 to 2, which we can cancel down to 1 to 1. When we swap and drop that, we can see the ones are just going to cancel, and so copper carbonate is just CuCO3. Sulfuric acid, you should know by now, is H2SO4. And copper sulfate we need to do our swap and drop for. So copper again is Cu, sulfate is SO4, as we've seen with previous reactions, so it's SO4 2-. First thing I do is write down everything bar the charge, so that's SO and including the 4 at the end. I then get my valency from the charge, which is 2-, so my valency is 2. Again, my valency of copper hasn't changed, so it is 2 also. Again, that cancels down to 1 to 1. And when I swap and drop, I'm just going to end up with CuSO4. I also have water, and I have carbon dioxide. Carbon dioxide is CO2. We know that because it's carbon, which is C, and then di means 2, and oxide means oxygen. So 1 carbon and 2 oxygens. So let's make a list to see if this is balanced. So I've got copper, I've got carbon, I've got oxygen, I've got hydrogen, and I've got sulfur. I write that list then on the right hand side as well. Copper, carbon, oxygen, hydrogen and sulfur. On the left we can see that I've got 1 copper, I've got 1 carbon. I need to be careful with my oxygens. I've got 3 here and then 4 here, which is 7. Hydrogens, I've got 2 here, and sulfurs, I've got 1. On the right hand side then we can see that again I've got 1 copper, just 1 carbon. Oxygens, I need to be careful. I've got 4 here, plus 1 here, plus 2 here, which is 7. Hydrogens, I've got 2 here, and sulfurs, I've got 1. So we can see from this equation, list, that our equation is already balanced, and so we don't need to do anything more with it. So just be really careful, particularly with your carbonate ion. And we'll have a look at that in our next example. Our next example is calcium carbonate and hydrochloric acid. What I want you to do is pause the video and give that a go, and then I will go over it. So with this example, again, I need to keep my general equation in mind. The first thing I produce is a salt, and I need to name that salt. First part of the name comes from the metal, which is calcium. Second part of the name comes from the acid. The acid is hydrochloric acid, so that changes its ending to chloride. I then look to my general equation and see that I also form water, and I also form carbon dioxide, just as the example above. Okay, the first stage in writing my balance symbol equation is doing my swap and drop to get my formula. So first of all, we have calcium carbonate. Calcium is simply just Ca. Carbonate, I need to think about a little bit. Carbonate is CO3, 2-, that appears in the back of your periodic table. First thing I need to do is write down everything, bar the charge, including that little 3 at the end. So it's really important that you remember that. So I write down CO3. I then look to my valency, or my charge for my valency. My charge is 2-, and so my valency is 2. Calcium is in group 2, so its valency is also 2. I can see that ratio of 2 to 2 will cancel down to 1 to 1. And so I end up with my formula of calcium carbonate, after I do my swap and drop, is simply CaCO3, because those ones are just going to cancel out. CaCO3. Hydrochloric acid is simply HCl, you should know that by now. And then I form my salt, which is calcium chloride. Again, don't overcomplicate this, we simply use calcium and chlorine. Calcium is Ca, chlorine is Cl. My valency of calcium is 2 because it's in group 2, and my valency of chloride is 1 because it's in group 7. When I swap and drop those, you can see that the 2 swaps over to my chlorine and the 1 swaps over to my calcium, and so I end up with CaCl2. I then form water and carbon dioxide, which is CO2. You should know that by now, but we can also see it from the name. Carbon, 1 carbon, dioxide, which means 2 oxygens. I need to balance my equation now, and so to do that I make a list firstly of all the elements I have. So I have calcium, I have carbon, I have oxygen, I have hydrogen, and I have chlorine. And I write that list on the other side in exactly the same order. Now to count up how many of each I have 1 calcium, 1 carbon, 3 oxygens, 1 hydrogen, and 1 chlorine. On the right hand side I have 1 calcium, I have 1 carbon, I have 1 plus my 2 oxygens, which is 3, and I have 2 hydrogens, and I have 2 chlorines. So we can see that the only things that are unbalanced are hydrogen and chlorine, and I fix that very easily by just putting a 2 in front of my HCl, which means I now have 2 hydrogens and also 2 chlorines. Okay, so take that step by step, take your time with writing those equations, thinking about what you're forming, and then writing your symbol equation from that. The rest of this page simply talks about how we test for carbon dioxide. So remember when we had a metal reacting with an acid, we produced hydrogen as a gas. How did we test for hydrogen? Well, it is the Squeaky Pop Test, and remember that we write down that you apply a lighted splint and a popping sound will result. Here we've got a different gas being produced with the metal carbonate, it's an acid, and that's carbon dioxide. The test for carbon dioxide is not the Squeaky Pop test, but instead it's lime water solution. So you can see here I've got exactly what my second reaction was, calcium carbonate reacting with hydrochloric acid. And what happens is the calcium carbonate, it will start to fizz because it's producing carbon dioxide. That carbon dioxide will come up, it will pass through this delivery tube and into the solution of lime water. Lime water is colourless originally, But when carbon dioxide gas is bubbled through it, it turns milky or cloudy. And this is your main observation that you want to write if you were asked how to test for carbon dioxide. So the test for carbon dioxide is that you pass carbon dioxide through a solution of lime water, and that's here. And lime water turns from colourless to milky if the gas is carbon dioxide. If the gas was hydrogen, like we saw before, lime water would just remain colourless. But that's the main colour change you need to learn here. Lime water changes from colourless to milky in the presence of carbon dioxide. So that's a way of confirming that this compound was a metal carbonate, because we know that a metal carbonate and acid produces carbon dioxide. And so if my lime water changes from colourless to milky, I know that I've produced carbon dioxide and that must have come from a carbonate. The very last part of this topic requires you to know the colours of the salts, and the only thing that can come up on this question is literally you having to state or maybe fill in a table with the colour of these salts. So it might be a good idea to colour code your notes a little bit. The copper, we can see here that copper salts have a different colour depending on whether they're in solution or whether they are just a solid. So copper oxide is a solid, and it's the reaction I did in class just yesterday with the black copper oxide powder. So it's a solid and it is black. Copper carbonate, we'll see on Tuesday, is a nice green colour. Again, it is a solid, it's a powder. So these two solids of copper are different colours. What we see with hydrated copper sulfate, that is sort of nice crystals of copper sulfate, is that they are blue, and copper salts in solution are blue. So if we have any solution of copper, be that copper chloride, copper sulfate, copper nitrate, it is blue. So you need to just learn those colours. With the rest of the salts that you need to know of, it's very simply that they are all white. So if they're copper, it depends which copper they are, whether it's copper oxide, copper carbonate, or copper sulfate. But with group 1, group 2, and aluminium, which is in group 3, for salts of those, they are all white. So think of group 1 salts, for example, would be sodium chloride, which is NaCl. Sodium chloride is your table salt, and it's just white. What happens when you dissolve table salt in water? You get a colourless solution. So for those group 1, group 2 and aluminium salts, they all are white solids. They form colourless solutions. How a question like that would come up, they would give you a specific one. So say they might give you magnesium bromide. They might ask you, what colour is magnesium bromide? And you'd think, I haven't a clue. But you need to think back. Okay, well, magnesium is in group 2. And so it forms a white salt. If I then dissolved it in water, it would form a colourless solution. What about if it was aluminium oxide, Al2O3? You think, I don't know what colour aluminium oxide is. Well, what I do know is that aluminium salts are all white, and so aluminium oxide must be white. And when I dissolve it in water, it must form a colourless solution. So those are general rules that you're learning for group 1, group 2 and aluminium salts, but you need to be able to apply them to specific examples. So that's the end of this topic. The key thing that I want you to take away from here is your general equations. I'll write them here now, but you should, on a piece of paper, practice writing them and learn them off by heart. And when you get into an exam, I would really advise that you take a piece of paper and you write down your 3 general equations just before you start answering any questions. It means if this comes up, you can look to them. So firstly, you've got a metal on its own reacting with acid. What's your general products for that? Well, we always get a salt, but this time our side product is just hydrogen. Okay. The next one we saw was a metal oxide or hydroxide. Reacting with acid. This time we produce a salt, but then I need to think about my side products, which this time is water. Then the last one we saw was a metal carbonate plus acid. That reacts to give us again a salt, plus, and then I need to think about my side products. This time it is water. And then because I've got carbonate, I'm going to get carbon dioxide given off.